Good afternoon, 8th and ninth grade. This is the lesson that we've been waiting for. We are ready for page 411 and we will finish the book. Woo! That's a good feeling. Today we're still talking about stars. We're talking about galaxies. We're talking about space, universe. And we talk about distance. And if you've never been to, let me see, there are planetariums around here. There's one in the Science Museum in Missouri, in St. Louis, where you want to go on a field trip. We didn't go, of course, and there's one there. There's one at the Creation Museum in Ken Ham's Creation Museum in Cincinnati, or over by Cincinnati, Ohio. There's others around here. I think there's one in Indianapolis. But it helps you get a picture of how the universe is made, and it's vast, or it's huge, or it's big, and all those words don't describe it. Now today we're going to talk about just a few little technical things about galaxies, as well as about measuring the distance of stars. You know, they talk about how far something is, and you know, here for us, if you ask, how far is it from your house to my house? Well, I don't know, but we'll go there and find out, and then we'll check the mileage. Or you might ask, how far is it from your house to school? Well, you have gone off, or you have went back and forth often enough that you know how far it is because you look. Now, how can we say how far it is to that star when we've never gone there? Or how far it is to that galaxy and we've never gone there? How do you reckon with that? And especially the stars. How far away the stars are? Well, look at your diagram on 411. Down on the bottom, you have the Earth traveling around the sun. And then you have the star down here in the right-hand corner. And so I won't go through to explain to you, but if you use geometry in the degrees, if you have two different measurements, you can find the third. You know that. Okay? Matter of fact is, if you have a one measurement and degree, you can calculate the others. They have 2 degrees, okay? And then they have a point, and they use those 2 degrees to tell the distance. It's not really that hard. It's just simple math. And that works great for stars that are relatively close in comparison to the size of our Earth. But you remember, our Earth is little and stars are big. And so it works good whenever you're doing it just right here. This dot right here, let's say this is Earth and the star is out here. And so as the Earth spins around, let's do it. We get too big here. Let's narrow this down. We have Earth, and then we have the sun, and then we're going to put the star right over here. Okay? Well, you can barely see that now. Let's try this one here. Here's the star. Here's the sun. Here's our Earth. And so we can get this here distance right here, or we can measure here, and then as we travel in our path around, 6 months later, we can do it here, and we can get this here, and we say, oh, from here to here, we know how far we are, so we say, okay, we can figure that out. That's not so hard. But you see what happens? If you put that star way, what you can't see me, I'm way over here, then your lines, your degrees are much flatter. You see what I mean? To get out here to this star way over there. And so you have almost no variation in your 2 degrees. So it's not the perfect match, a way to measure a star. Now you have 2 ways. Do you see the parallax method and the apparent magnitude method? Okay, now there's another way. This is a parallax method, and it works great on close stars. Now, if you want to do something far away, you can use the apparent magnitude. That's how bright the star is. So turn your page to 412, and it says how the parallax method. How far out does the parallax method work? Well, it says it's about a light year. So we're going to start using light years. Okay. Now let me stop. A light year is how fast light will travel in any given direction. Okay. Now remember, light. We said what's the fastest thing that travels? The fastest car, the fastest the fastest plane, and then we said, oh, light is the fastest part of matter. Light travels the fastest of all matter. We learned that earlier. Now here again, we're going to say we're going to use light years to see how far this star is out here, or out there, or out there. Okay. Now get this. Light travels at I'm in the middle of page 412. It travels 300 million meters per second. So 300 million meters per second. How far would it go in an hour or in a day? And now we say a year. Well, it says it's just under 6 trillion miles a year. Just 6 trillion. Okay, a million miles is a lot. But 6 trillion, you got a million and a billion, a trillion miles. Well, I'm kind of getting kind of a foggy comprehension of how far away that is. And then we say that we are in a galaxy, and our galaxy is 100. I'm on the second to the last paragraph on 412. It says it's 100 light years diameter. 100,000 light years diameter. Okay, the Earth is not 100,000 years old. How you like that? Well, no, I don't believe in evolution. 100,000 light years, and the Earth is only 6,000 years old. How can you get 100? Can you imagine? Light couldn't even travel all the way across the galaxy since time began. Woo! You get a little picture? Now our galaxy is only 3,000 light years deep, but it's a spiral. Oh, that brings me to the next part. I jumped over to 413. I never really talked about the magnitude there was a lady, Henrietta Leavitt, I'm not sure how, Leavitt, it's not pronounced, so I'm not sure. She is the one that discovered how to use the apparent magnitude method to distance stars to see how bright they are, and you can tell how far away by how bright they are. That's found on top of 413. It says, after all, if you have a way of calculating the absolute magnitude of a star, then you can measure the amount of light that it makes to the Earth from the star. This is very easy to determine how far away the star is. If you know the magnitude, you can easily detect how far away it is because it's not as bright. But the problem is, how do you know the magnitude? You see, the trick is, of course, is knowing the absolute magnitude of the star to begin with. How do you know for sure the magnitude of that star? And that's hard to figure. We have to take a guess. Our scientists have to take a guess. If they could get the magnitude right, they could get the distance right. But the problem is the apparent magnitude is not a reliable way to measure a star because it's so far away. We've never been there. Yeah, you got the point. It's too big. Space is too big. Yeah, you answer that question. Which distance measuring method is the most reliable? The parallax method or the apparent magnitude method? And I just got done telling you that, oh, that's your question answer. I better not tell you. Let's go to the next part. It's galaxies. Galaxies are, the stars aren't just out there, one here, one there, one over there. Well, you look up in the sky and you see a whole sky full of them. But really they're arranged in groups, in clusters, called galaxies. And now I'm back up here to our galaxy is the Milky Way. And there are three types of galaxies. On the bottom of 313, you see the spiral galaxy, the lenticular galaxy, and the elliptical galaxy. So basically, you have the spiral galaxy is like a flat, like ours, and it's got tails out. And our sun is out in one of those tails. That's interesting. We're not even close to the center of our galaxy. But from one side of our galaxy to the other side is 100, get this right, 100,000 light years. Lenticular galaxies are just like a flat disc without the tails. They're similar to the spiral, but they don't have the tails. And then the elliptical galaxies are those round balls. They're like, think of it like a ball. A whole group of clusters in a ball. And they all have a nucleus. A nucleus is a center, like an atom. Well, these galaxies have a nucleus that's bright. A center of tightly clustered stars makes a bright light. Okay, turn to page 2, 414. Okay. Then you also have a group of irregular galaxies. That's on top of 414. I never even got to that one. They don't have any shape at all. So we just say they're irregular ones. Now remember how big ours is, 100,000 light years ours is, and then there's a whole bunch of others out there. Now, you go down on 413 and it says, they're not just scattered out there, thrown out there however they come out, they're kind of arranged in groups. Whoa. Okay, our solar system is around our sun, one sun, and then our sun is in a group of other suns or stars or galaxies, however you want to say it, and we form a galaxy. And then from there, from forming the galaxies, you have, on the middle of 414, it tells you that you have what we call a local group. So there's 30 galaxies in our local group. So Milky Way is one of them, and 30 more, or 29 more. I don't know all their names. I don't know any of their names, okay? I can't even tell you any of their names. And then from there, we have the Virgo group. Okay, our local group of galaxies is in the viral group of galaxies. I said, oh boy, that's about enough, right? No, he said there's another. Our viral group is in a supercluster. Woo! So back up here. Are you lost yet? I'm lost. Let me see if I can get all the steps. We have our Earth and the solar system around the sun. And then we have the Milky Way, and then we have our local group of 30 galaxies, and then we have our local group is a part of the Virgo group, and then from the Virgo group, we're part of the supercluster. And there's a whole bunch of superclusters in space. It blows my mind. It blows my mind. Is it yours? You got a young mind, so maybe it doesn't blow yours. I can't fathom. I can't fathom stars, galaxies, and how far they are. And then he says, on the very bottom, the distribution of these galaxies and clusters in the portion of the universe we are able to observe is not uniform. We just don't know if these are in order or how. Instead, they tend to form a long, stringy, almost lace-like filaments that arrange around large voids, okay? So we just got little streams of galaxies out through space, and there's big voids out there, big empty spaces. One of these filaments is called the Great Wall, stretches across more than 500 million light years in space. Okay, there's some of these galaxies that are stretching out there 500 million light years in space. This long wall. It's called the Great Wall. Let that be. Now we're going to jump to something different. We talked about stars, how far away they are. We talked about groups of stars called galaxies. Now, in page 15, we're going to start talking about, he starts to explain, okay, now this is a pretty big thing, but he starts talking about the wavelength that's coming from other planets, no, not planets, from other stars. It's kind of got a red shift. He calls it a red shift on 15. and it's got longer wavelengths, kind of red. And this is puzzling scientists. Why is this doing this way? And then he says, oh, you remember what we talked about back here in Unit 14 about the wavelengths, the red wavelength, they're longer. And he says that is like visible light whenever he talks about the drop effect. When it moves, they kind of bunch up. Okay, you know, like sound. Sound would do this. Okay, light does the same thing. It moves and it bunches up. Well, just like sound, you know, remember the question about the car that was blowing the horn as it was coming towards us. It made different sound than when after it left us. Okay, light does the same thing. And it makes different rays, wavelengths, depending on where you're at. And so with this here, there's kind of this red glow that things are moving. And now, don't panic. It's not moving toward us, it's moving away from us. Or that's one theory. Now, we'll talk about that here just in a moment. There are actually 3 different theories that could be. You could say the universe is expanding, and the farther the galaxy is from the Earth, the larger the red shift. Okay, so it's kind of the light that's coming from the galaxy has kind of got a red shift. That's because it's moving. Okay, now there is 2 ways. It could be that the Earth, no, there's 3 ways. It could be that the Earth is the center and everything's moving, or our solar system is the center, everything's moving away. Or it could just simply be that there's an expansion. Everything is moving proportionally away from each other. And that there is no fixed center. Okay, that's possible. Regardless of how it is, scientists believe that there is an expansion. So turn your page to 416 and we'll look at that example, the expansion. This is a pretty simple one, and I'm afraid you won't do it at home. Matter of fact is, there's only about 1 of you that ever does any experiments that have told me about it. Maybe the rest of you are doing it and you don't tell me about it. So I will do this expansion here. You need a balloon, a marker, you need to be able to write on the balloon. So this side of the balloon says happy birthday, but I'll write on the back side of the balloon. I just made some dots. And we're going to pretend like these are galaxies. And I don't know which ones they are. Oh yeah, the one's got a tail. You see that one there? And I assumed that there was a Milky Way galaxy right there. And so if there is no center, let me show you how these expand. They're fairly close together. They're all within an inch. Okay? If you measure these here, an inch apart. Now you can see our Milky Way. It's pretty clear now. It's got a big tail there. See how, are those an inch apart now? No, they're more like 2 inches apart. They're expanding. Now you see how those galaxies will continue to expand? Now I'm thinking the sun is out here in one of these, right out here in this tail, right out here is where the sun is. So we're out here in this part here of the galaxy. And these others will keep expanding. See, there is no center. It just keeps going bigger and bigger and bigger. That is also a possibility. Number 1, there could be a center. There could be a center, and all the galaxies are moving out from the center point. It could be the Earth. We'll assume that it's the Earth, and they're moving away from us. Or there could be no center, like the balloon. There is no center. They just continue to move out from each other. And then number 3 on top of 417. Once again, this is a perfect consistent with the data we have. Finally, it might not be expanding at all. See, we're just going by the red shift that we're getting from the light, and we might be wrong. That red shift could be coming from something else. Remember, the expansion of the universe is a result of interpretation of the red shift. It is possible that the interpretation is wrong. There could be no expansion. We might be wrong. Oh. Now, let's talk about what if there was a Pacific special place, and we're going to assume that the Earth would be that space. You see, a lot of scientists don't like that because they say it was just a big boom and everything just from that big boom just keeps expanding. That makes sense? So they don't want to recognize that there is a special place, that there is a beginning point, that God created the world, God created the universe, God created the galaxies and the stars. We don't know. It makes sense why they don't want to believe a special place. They want to believe in this theory. And again, it's neither theory is with the data that we can collect here on earth. Neither theory is right or wrong. Each has as much evidence as the other one to support it to be right. There is a problem though that we have discussed, and it's found on the bottom. If we believe that the earth is only 6,000 years old, how did the light ever get to here? How do we see stars light from only 6,000 years old? It would take billions of years for the light to reach us to get here. Well, Dr. Murphy's theory explains this problem. Okay, Dr. Murphy was a man that lived back, I don't even know his name. What did it tell? He lived before Einstein. Murphy, he wrote a book, Starlight in Time. He says, read that book, A Starlight in Time, if you want to. I don't know the book. I haven't read it. I've heard of it, though. Let me see. Murphy shows that if the universe is expanding with the Earth's solar system as its center, creation would only have happened a few thousand years ago, and we would still be able to see light that took billions of years to travel here. As I said before, the details of Dr. Murphy's theory are beyond the scope of this course. However, the point I want to make is rather simple. The majority of the scientists that believe in this theory called the Big Bang, the theory assumes the universe is expanding, but assumes that expansion is taking place without a center. Okay? You get the point why they believe that way. And he says, whether the universe is expanding around a fixed center with no center at all, or in some other way I did not discuss, so we don't even know, so there might be some other ways it's expanding. The majority of astrologers think that it is expanding. Okay? We don't know the way, the method, or why, but it does appear like it's expanding. And then he says, oh, that's nothing. In Job 9, verse 5 to 8, he says, who alone stretches out the heavens? Who stretches the heavens? Job says. Now, while man has studied for thousands of years and have studied the stars, I mean, we're by far not the first people to study stars. Even the Egyptians back years ago studied that, thousands of years ago. What man is just realizing today is what the Bible said back in Job's day. The earth is stretching out. The heavens are being stretched out. The planets and the galaxies are being stretched out. Well, that concludes our study. I hope that you are ready for a study guide on Monday, and then if you're ready for that, you can do test on Tuesday, or you can do test on Wednesday like the schedule says. I'm sending the test home this weekend, so when you get the study guide finished, you're ready to go for tests. So you set your own schedule. Please do it by Wednesday, and we'll go from there. Have a good one.